Right, welcome everyone. Thanks for coming to my talk. Late on the second day of the conference, that's always a nice thing to see a lot of people in. We'll be talking about backend technologies for the front-end developer. Hopefully that is exciting to you. I mean, you come here, so hopefully that is the case. So let's start with the mandatory who I am. My name is Savvas Dalkitsis. I'm the principal engineer for apps at ASUS. I basically look after both Android and iOS, even though really I'm an Android developer, but don't tell our iOS developers that. And yeah, don't worry about the links both here and later on. All these slides will be basically shared at the end, so you can grab them from the presentation. Right, so who we are, we're ASUS. For those that might not know, we're a fashion company. We're technically, I'll read you our tagline. Our vision is to be the world's #1 fashion destination for fashion-loving 20-somethings. Sounds maybe not so much interesting to many of you, but one of the things that might not be super obvious about ASUS is that we're a very technology-focused company because we don't have any retail stores. We're basically only online. And that, of course, means that the primary driver for revenue in our company is technology. And it just so happens to be that mobile apps are the main revenue driver for ASUS. Yeah, you can follow the QR code there to find more stuff about us. So why are you here? Like, okay, what's the point of backend technologies, and why do we even need this talk? Okay, so let's have a look at the technologies that we might all be familiar with, right? So I would be hard-pressed to find anyone in this room that doesn't know at least 99% of the words on this slide. It's kind of standard stuff for a mobile development lifecycle. But you might not be familiar with any or maybe some of the words in this slide. These are more like backend stuff that you might be familiar with, but not use in your day-to-day. So what? I don't need to do that. I'm a mobile developer, right? I build apps for a living. Well, as the slide describes, you want to be able to have a basic understanding of the language that other team members in your company or in your domain use, so you can have intelligent discussions with them. How frustrating is it when you speak with a backend engineer and they don't quite understand how apps work? They talk about deployments, like have you scaled up your apps and they don't quite understand that the app is actually on the user's phone? Now flip that and see how frustrated they are when you have no idea how they deploy the software. So this is hopefully a way to expose you to this area of the world if you haven't already been exposed, and hopefully will help you be a better engineer, especially as you climb the seniority ladder, because part of being a senior engineer is to be an enabler for your team to the other stakeholders in your company. So let's start. I'm going to group some of these technologies under various really big, wide umbrellas. They might not be very grouped together in a coherent way, but hopefully we'll get to the end making sense of what we're talking about. So let's start with something that is actually quite applicable to front-end. Even though it has to do slightly with the back-end, it's something that I, in personal opinion, think that every engineer should know, regardless of the seniority, and that is caching, right? This whole talk basically started off from this point. During my interview days, let's say, I've met a lot of people, spoken with a lot of devs in various different seniority levels, and one common thread that I found amongst them is that, again, not everyone, but a lot of people that maybe have worked for like 10 years doing Android, they're not really familiar with how caching works, and not just caching inside the app, which you might all be familiar with, but generally, why is caching, like you see the quote there, it's supposed to be like one of the hardest problems, right? Why? It seems fairly straightforward. You cache something, you don't get it from the network again. What's so hard about that? Well, let's see. First, let's talk about expiry headers. This is potentially the most important, I think, topic that you should get out of my talk if you only get one thing out of it. It's basically expiry headers. So think about a very standard structure. This is a fairly typical architecture for apps. You should all be familiar with it. Don't worry too much about the details of the diagram, but effectively your app needs to make some sort of call. You check your local cache, is it there? Yes, no. If it isn't, you get it from the network, you put it in the cache, you give it to your view or whoever asked for it, right? Fairly standard thing. But what is that in cache? Like, is that just a question of, is it in the cache? Okay, if it's in the cache, is it there forever? Do you just keep everything in the cache? How long do you keep items, or how many items do you keep? We've had a bug, I remember once in our app, I'm looking at my old colleagues there who might remember it, where we weren't clearing the image cache properly in our app, and we ended up with some of our most, let's say, enthusiastic customers having like 2 gigabytes of data taken out of their phone just because they browse the app so much, right? We weren't evicting them properly. So what do you do? Like, how do you get rid of these images? Well, there's many strategies. One could be literally, I don't know, keep, I don't know, 100 items, and that's it, and then just cycle them through. So newer items will evict older items in. That's kind of like a FIFO type eviction strategy. Another one would be just rely on the size. So just say, I want, I don't know, 100 megabytes of data. Whenever I reach that, I will then go and evict some random things, or again, the oldest, or you can combine them. All of these things have their value. They're useful for specific use cases, but they tend to be the wrong choice for general purpose caching in apps. And the reason for that is that they're very inflexible. They basically put you in a specific mode, and that's it. For example, I want my avatar image to refresh more frequently than, let's say, a product image. You know, a product image might be valid for a day or two, or might be even for a week. But you might change your avatar profile, I don't know, every 10 minutes, right? So that requires you to, in your app, know the type of images you're loading so that you can make informed decisions on the caching strategy of them, which makes things complicated and not very fun. So how do you solve this? Well, you use server-side controlled expiry. You don't know what an image is. The server does. So you don't care about it. You basically say, hey, I'm going to download an image, and you tell me how long I should keep it for. And therefore, magically, you have the best of both worlds. A, you have to do less work, which is great. And B, the server can actually tell you how long an image should be valid for, right? And again, this is a very deep topic. We'll just skim the surface of it. But that's the basic idea. You let the server tell you. How do you do that? By using headers. This header, the expires header, tells you literally the date and time when an asset, and again, I'm talking about images here, but this could be anything, any JSON response, anything, when it should expire. So you store that image, well, you store that date next to whatever you downloaded, and you just check. But again, that's kind of inflexible because it's basically hard coding a specific timing for that asset. There are newer headers, and those are the ones that you will probably be familiar, well, you will probably end up using. That's the new one. New one, by saying new, it's like, you know, a decade old and more. It's the cache control header. This is super flexible because it doesn't specify a specific format for the value of it. It doesn't say this expires on that date. It has a lot of directives, like that max age value that you see here is one of the multiple directives that this specific case will tell you this will live for, I don't know, 604,800 seconds, which is, I'm not going to do the math. But this is one of the most common headers you will find. And you typically store that again with your asset and the time that you downloaded it, so it's like a relative date. This is also a dynamic value that usually changes. If you ask for the same asset again, you'll get a different value. These are all the directives. Don't focus too much on the details, but you can see there's a lot of them. And it's also, the most important thing here is that this is also a request and response header. So from your app, you can direct the server to say, hey, give me this image, but only if I don't know, it hasn't been stale for 3 days or something like that. So you also have control in that. And the server can then take smart decisions based on what you ask it. It's not a guarantee, obviously. The headers that you send are kind of like a suggestion. But yeah, as you can see, there's like lots of them, and they enable lots of really cool functionality. One of my favorite ones, which of course we implemented at ASUS, is the stale if error, right? So when you request an image, you can send this header and basically ask your networking library, might be OKHTTP or whatever you use, to fetch things from the cache, even if they've expired, if there's a network error. So even if an image has expired, if for whatever reason you can't get it from the network, you still want to show it to the user. For instance, in products, that makes sense. In your use case, it might not. So you get to decide what you want to do. So those are kind of like the two important ones that you might find useful. Do go to the link that I provide and read up on the rest. There's a lot of really cool functionality type things that you can implement with this. E-tags, show of hands. Who here has heard of or knows what an e-tag is? Okay. Few people, as expected, but not no one, which is nice. An e-tag is a very interesting concept. It's basically, like it's a response header as an identifier, blah, blah, blah. Technical definitions are boring. It's there, and you can read more about it from the link. What it actually is, it's a unique resource ID, right? So the idea is, whenever you request a resource, if you're getting it from the server, or if it's a resource that you produce, you accompany it with a universal unique ID, right? And it's a UUID, kind of like a standard thing that most of us should know about. And when you get a resource from the network, like an image, it will be accompanied by an e-tag, along with those expiry headers that I mentioned. And the idea with this resource is that it allows you to refresh stale resources. So when an image, in this scenario here, has expired, when you get it from your local cache, you also get its e-tag value with it. And then when you make the network request again, you send the e-tag that you had saved previously, and you send it with the if non-match header. You basically say, give me this image, if non-match this UUID. If the server hasn't changed the image in the meantime, it will know that. It will compare the UUIDs, and instead of giving you the data again, so you have to download a new image, it just gives you, this is a refresh thing. I think it's a 304, yeah. A 304 called not modified, with the new expiry headers. And all your client will have to do is refresh the expiry date locally instead of re-downloading the image. So obviously that saves you data from downloading it, makes the client more battery efficient, all the good stuff that you would expect from not re-downloading an image. For the most part, these things are handled for you by whatever networking library you use. So if you use OKSTP, I think you get this out of the box. You don't get the previous stale if error thing. You have to do this yourself. But I think with the e-tags, you get them. But this is kind of like an interesting thing that you get for free, but it's useful to know how this caching thing works, right? So it solves another interesting use case. Have you ever thought what happens when both you and a coworker press submit on a wiki change that you make on the same page? Now, this is called a mid-air collision. You're basically both trying to modify the same resource at the same version of the resource. So, it's revision 1, and both of you try to make a revision 2. It's kind of, there you go. So this is the use case. You basically have two clients. They both make a request to submit to the server. The server gets the first request, writes it to the database, and before that operation submits and it receives the acknowledgement from the database layer or whatever it is, the second request comes in. So what do you do there? Well, the solution is, again, an e-tag. Basically, the server will respond back. When you make your submission, you will give it the resource ID, the e-tag of the resource you had as you had it when you tried to change it. And the server will tell you someone else has modified it or is in the middle of modifying it at the moment. And it will respond again with an if match header, and the code will be a 412 precondition failed. It will basically tell you, please try again or refresh. You may have seen that in, you try to submit something on a wiki and there's a JavaScript error saying, there's a newer version, so you have to press the refresh button. And then client side, you will try to resolve these conflicts by keeping the changes that you made and try to reapply them on the new version, right? So, okay, moving on to a wider view of caching. Does everyone here know what a CDN is? Okay, a few people. So a CDN is a content delivery network. It's basically a collection of servers around the world whose only purpose is to serve cached content to you faster than your own server would, right? So the idea is that it sits between your origin server, and you. So when you ask for a resource, as you can see here in the time diagram, you get the resource, the CDN doesn't have it, so it asks your origin server, hey, someone's asking for this thing. Your server gets it from somewhere, a database or whatever, returns it to the CDN, and the CDN caches it. Now, there's different headers for controlling that side of the caching. So there's the caching from CDN to origin. Again, you can find those in the directives in the previous page that I showed you. But the CDN caches it, returns it to you, and the next time you get it from the CDN. You don't have to actually go to your origin server. And the reason you would do that is speed. CDNs tend to be very optimized for fast delivery of static assets, and it's less costly. You might be surprised as front-end engineers to learn that database access is quite expensive in the cloud. It is incredibly expensive to write and read, not just because of the act of writing and reading itself, it's because of multiple concurrent users. So, we have one user in our app, we're really lucky in that sense, but a service might have like 10,000 concurrent users, so they have to deal with all that traffic. So the more of that traffic you can remove from your server, the better it is, right? And that's what a CDN will do. The type of things that a CDN will cache is images, obviously. But it will also stack anything that is static that doesn't change that frequently. So it might be like scripts that your web page loads, whatever, basically. Maybe yeah, it can also cache web pages, which is very important, which brings us to server-side render pages. How many of you have thought of what happens when you actually load a web page? Like, it's kind of a simplistic question. You get a web page back, right? What's so special about it? But what exactly are you getting? Are you getting the full HTML of the page every single time? Or do you get something that then dynamically loads data? So in our example here, we're loading the search page of ASOS, right? We're searching for jeans. Do we download the entire web page with the whole HTML in one go? So does the server render the entire page and give it to us? Or do we just load the scaffolding of the page, and then we have JavaScript in the browser loading the actual data that we display? Well, we do a bit of both. And this is specifically for ASUS, by the way, but everyone kind of does this. The idea here is that, okay, we know that a lot of people are searching for jeans. 90% of them will stay on the first page. They won't actually scroll to the bottom to load more data. So what you do, you have your server, the web page in this case, render the first page of search results, and ask the CDN to cache it for, I don't know, like 10 minutes or something. It doesn't even have to be that long to actually reduce the traffic to your origin, right? So when you or me search for jeans, we get the result from the CDN with the actual rendered content. And then for the few of us that scroll, when we get to the bottom of the page, the JavaScript on the page will load the next set of data and actually load them dynamically into the page. That data is also potentially cached on its own way, but it doesn't come back as part of the original response, let's say. So when you hear server-side rendered pages, that's what we mean. It literally is the content is rendered server-side, and you get a cached version of it versus doing JavaScript manipulation on the actual browser. And again, the reason for that is cost. Like I mentioned before, 90% of the people will not actually scroll past the first page, so you can save a humongous amount of traffic hitting your origin server, which would require you making API calls to other services that will in turn do database calls, right? So that's how you basically offset the cost of really costly API calls. So hopefully that gives you a general idea of how multi-layered caching works. Like caching exists in every layer from the database in your app to your in-memory cache, to your CDN, to the origin. The origin has its own caches. So there's like a huge step of caches. And managing when they invalidate themselves is why caching is the most difficult problem in computing, like we saw in the first slide. So yeah, this is a very rough overview of how a multi-layered caching system would work. You can see here from your user, you're asking the app for data. The app will ask the in-memory cache, which will in turn ask the persisted cache, which will then return the data up to the app. If it doesn't have it, the app will ask the CDN. The CDN will ask your origin server. The origin server will ask its own in-memory cache, which might be a literal just in-memory data structure like we do in apps, or it might be another service that runs. Usually it would be like Redis or Memcache. There's a lot of solutions out there. And that in turn, if it doesn't exist, it will go to more persistent storage like a SQL database or some other non-SQL database. And you can see the whole data flow basically going up and down. And all these layers have caching. So being aware of them is quite helpful. You don't have to know all the details, obviously, but understanding them is kind of an important thing. So yeah, let's move on from caching to web application and API design. These are principles that you should be vaguely familiar with. You don't have to be an expert. I'm not an expert in these things, obviously. Like, I'm a mobile developer. That's what I do. But being aware of these things, when I speak with our web people, it's helpful, like I mentioned before, to know what they're talking about. And I'm not completely lost in these discussions. So let's start by talking about REST. Hopefully, many of you have heard of the term REST. Many companies claim they do REST, but they do a version of REST, but it's kind of like MVP or MVVM. You know how everyone says, well, we do MVVM, but it's not really MVVM. There's always flavors, right? And the reason for that is because REST is not actually a standard. It's a set of architectural constraints, but there's no actual set, like, rule book of this is REST. There are many opinions of what REST is. You can find more in that link that I shared. And like any other discussion about architectural design, it tends to be kind of like ideological and no, this is the right way to do it. No, that's the right way to do it. I won't focus on any of that. I want to focus on a couple of things that are actually practical reasons why REST should be done a specific way. And I will explain why I think these reasons are sensible. So let's start by HTTP verbs. So the idea is that every time you interact with an HTTP-based API, ignore GraphQL for a moment, is that you're basically doing transactions. You're reading stuff, you're updating stuff, you're adding stuff, you're deleting stuff. These are kind of standard things that HTTP and REST are built for, right? How many of you have seen something like this? Right? You have like 4 different API endpoints there, one for adding address, another one for getting an address, changing and deleting. This is far too common. Just don't. I know you're not designing your APIs in the company that you work for or in your project, but if you do see these things in your area, try to have an intelligent discussion with whoever is maintaining that team and see, can we improve this in the future? And the reason for improving them is because HTTP verbs are called verbs for a reason. In REST, HTTP are the verbs and REST resources are the nouns. So instead of adding an address, you post to the address resource. Instead of getting an address, you get, like HTTP get, the address resource. So the resource stays the same. You just perform different verbs on it. Obviously you have more stuff like patch options. There's like lots of things. I'm not going to obviously go into details of that. But that is not just an ideological preference. Obviously, it looks nicer in my opinion as well. It's easier to grok as well. Some people might go, okay, there's the address API. That's it. And then I know that I can post, read, put, whatever I want to do on it. But it's also practical. HTTP has a standard, and it's implemented by everything from your device all the way to the database that your server is using. There's a lot of middleware sitting there. There's a lot of services that basically receive traffic and redirect it to other things. We'll talk about that a bit later on. But all these layers respect the HTTP spec. And some of those definitions, what they do is they might avoid actually redirecting traffic to your service. Some of these calls here, I think the get, the put, and the delete, again, we'll talk about that in a bit, might not even make it to your server if you do them twice in a row. And that's a good reason. There's a good reason for that, which will save you money. But more importantly, if you're abusing the verbs, if we go back to the previous slide, I've seen APIs designed to require a get call, like a get HTTP call, to the add address API. That's not just bad design. That will cause problems because a middle layer somewhere that the server, whoever built the server doesn't control, will basically skip the call because it goes, well, I've already received this thing. I don't have to forward it, right? So this can cause actual problems. Again, I'll come back to that in a little bit, but let's talk about query parameters, something that you're all familiar with. We use query parameters all the time in our day-to-day jobs, but what you might not be aware of is that query parameters can be a security risk. They're not obviously always a security risk. We use them all the time, but they can be. So if you see something like this in the company that you work for or in your project, shout from the mountaintops, and I mean it, like you should not accept this. Passing username and passwords as query parameters is a security risk. You should literally refuse to implement this. The reason is, even though the query part of a request is actually encrypted during HTTPS calls, right? It's encrypted in transit, meaning that middleware, man-in-the-middle attacks cannot actually intercept that, so you're safe there. Again, those pesky middlewares that I mentioned before tend to have they have the tendency to log out the full request URLs that they receive when they forward them to other places. Now, there was a security incident a couple of years ago from a well-known financial fintech company, which obviously won't mention for obvious reasons, but what they had was a problem where people would try to update, I think it was their PIN or password, I can't remember what it was. And whoever designed the API happened to use query parameters. And of course, again, they were safe, but their middleware, which was sitting in potentially an unsecured server, that wasn't covered by PCI compliance, was basically logging these things just as they were coming in. So they were logging in plain text people's private information. And again, it's not just for passwords and security, it's also personal information. You don't want people's addresses to be printed out in plain text. So what I would suggest is that you send anything that is personally identifiable information or, again, PCI compliant information, you want to pass them either through headers or, even better, the body of the request. Again, there's no guarantee that these things will not be logged out, but to my knowledge, no self-respecting middleware will ever log out headers or body, at least in a production environment. Whereas query parameters, they might still do. So just basically, query parameters, bad. Let's talk about JWTs, another term that you may be vaguely familiar with. You've seen those, you may have worked with them, but what are they? Well, they're JSON web tokens. They're literally just a token that is a JSON file. A way to transmit signed pieces of information between services and usually backend and frontend, right? So, this is an example of a JWT. You can find this in jwt.io. So basically, what a JWT is literally just a collection of JSON blobs, usually two objects, with some required parameters and a lot of optional parameters. But you can put anything you want in there. And there are two types of JWTs. There are encrypted JWTs. I think they're called GETs. I can't remember the official name. And there are also signed ones. The signed ones are the ones that you would be most familiar with and interact with. A signed JWT is not encrypted. Anyone can decrypt it. So if I get it, because it's base 64, you literally have a base 64 encoded string. So anyone can just read that and read the content of it because they don't contain anything important. Well, I mean, they do, but they shouldn't contain anything that should be encrypted, let's say. The most important part of a JWT, a signed one, is the last bit, which is the signature of the sender. So in an ideal world, whenever you decode a JWT, you should be checking the signature of that JWT to verify that it matches the public signature of the server you're talking to. In practice, our apps don't really tend to do that because you control the JWTs, you control your storage. But in theory, if someone got access to the private storage area of your app, they could inject fake JWTs in there. And if you just read them randomly, they could inject potentially things that you shouldn't really be reading. So in theory, you should be checking the signature. Another thing that is very common in JWTs, and it's not part of the spec, sorry, it is part of the spec, but it's not a requirement of the spec, is an expiry date. So similar to the HTTP headers that we mentioned before, JWTs can expire. And most importantly, you can check that expiration without checking a third dependency. So you don't have to check with the server if this token is still valid. It will tell you when it expires. This allows very interesting use cases, and one of the most common ones that you are all familiar with, hopefully, is OAuth. Again, there's many flavors of OAuth. We'll talk about the most common one here. So an OAuth is, of course, an authentication mechanism, right? It allows you to talk to an authenticated endpoint without sending username and passwords. How does it do that? Right, so remember this URL that we talked about before? You want to avoid, well, I mean, even with the fixes that we mentioned, putting them in the header and the body, you still want to avoid doing that call as much as possible, because security is all about reducing the attack vector of whatever it is you're building. So reduce the amount of times you're sending the username and the password to a server, and you reduce the attack surface of your app, right? And the way you do that is instead of sending the password, you get a token back from the server once, and we'll talk about refreshing that token in a bit, but you use that token instead of the password. And that token is short-lived. So even if it leaks, an attacker might gain access to your app for like 10 seconds, which, again, further reduces the kind of damage that they can do. So OAuth works in a very simple way. Again, very deep topic, so don't take this as gospel. Do your own research, please, because I definitely just did not draw this in like 5 minutes. But basically, the idea is that your app says, OK, so I need to get authenticated. So when you log in, you talk to an identity server, and you say, hey, this is my username and password, and you set it in the body. And the server goes, OK, here's a refresh token. They usually send an access token as well, but some servers have been known not to do that, so I've described the more complicated flow here. So you get back the refresh token, and the refresh token is a long-lived token. It usually lives for like a month or something. Like, a server decides how long that lives, right? So you store that locally. And then you use that token to talk to that server again and say, hey, give me an access token. And the access token is a short-lived token. It might live for 10 seconds. It might live for a minute. Or, like I said, you get them both in the first call. And you save that as well. And that's the token, the access token, is the token that you use to talk to your actual server to make API calls. Now, because this token is very short-lived, at some point you're going to talk to it and it will expire. So how do you deal with that? Well, like I said, you can check locally if it has expired, which is one of the beauties of JWTs. Whenever you try to make an authenticated call, you can have an interceptor in there that checks its validity and go, oh, you're invalid. So before I make my call, I will just do another refresh. So at that point, you get the refresh token from your database or whatever. You do another refresh call to the identity server, which will give you a renewed access token. You save that and you use that. And that basically allows you to have these short-lived tokens that you expose to the wire. And if they get somehow magically intercepted by someone, they gain access to your basically account for just a tiny bit of time. And really well-designed APIs will have a really, really, really short time. Like I said, in the seconds. But of course, that then increases the network traffic. So you have to basically coordinate with your backend teams to make sure that you find a nice balance. Like, you don't want to be doing like thousands of calls every second to just refresh your tokens, right? So depending on your use case, that value might change. So then how do you, actually no, sorry, before we get to the how do you refresh it, which I think we've covered. What am I saying? Yeah, no. So this is another very, very useful flow that OAuth allows you to do. Have you ever seen the log out of all other devices button in some sites? Well, this is how it's done. You basically have a token, and when you press, log me out, or if the server decides, you know what, there's been a security breach, invalidate everyone's tokens. So what they do is they talk to your identity server. Again, there you go. So they talk to your identity server and say, invalidate all these tokens. If you ever see them, say they're invalid. So when you ask for an authenticated resource from your server, the server can either check locally, like you do on your side, if the token is valid, but they can alternatively also check with the identity server. And if the identity server tells them, that's invalid now, even if it says it's valid, they will return to you a 401, an authenticated one. And at that point, you're just going to do the dance again to refresh your token. So this allows you to remotely log people out of sessions that you don't have direct control over. There's also another edge case that a lot of people don't actually implement when they implement OAuth, which might actually trip a lot of you up. Hopefully, you can check your app if you do OAuth and check that it actually does this. The refresh token itself can technically expire. I said it's long-lived, but if you read the specs, many times they don't even mention it. They just say, keep this around and just keep refreshing. Whenever you refresh the access token, you might get a 401 at that point as well. And if you do that, you need to get rid of your refresh token. And at that point, you have to present some sort of login screen to the user again. So yeah, like you will have noticed a lot of sites, you log in and you say, remember me for 30 days. That's what they do. They basically say, OK, you have a long token for 30 days. And after that, you'll need to log in again. And at that point, you can decide, you know what, I will save the username and password locally, but encrypt it in the secured storage or whatever device your device has. And at that point, you can ask the user, I don't know, to use authentication with like biometrics or something to read the password again to avoid them having to type it. But again, that's a design choice that you will have to do. Now, what happens if you go through a tunnel? I asked this question in my interview process, so I always like to see how people react to it. What happens if you go through a tunnel just after you've sent like a purchase order to a site? So you go to ASOS, you put some JSON in your checkout, you press checkout, the server gets the request that you made, but before it responds to you, you go through the tunnel, so you lose connection. The server's gotten the response, it put it in its own queue or its own database. So as far as it's concerned, you've made a purchase, you haven't made a purchase. So when you exit the tunnel, it goes, there was an error, try again, and you press the button again. So you now basically have two purchases. So you've cost the customer twice. This is not a hypothetical problem. This has happened in a very well-known food delivery company that, again, I will not mention for obvious reasons, very recently. And it's a problem that will affect you too, potentially. And again, it's not just about purchasing things. Oh, I don't have purchases in my app. I'm good. Well, it could be something as innocuous as posting the same tweet twice. And this might even happen without the user's interaction. You might have an automatic retry logic in your client that says whenever there's an IO exception, just retry the request a few times. And that first IO exception might be because you've lost connectivity while the server has received it. So now you've magically posted the same tweet twice. So how do you solve this problem? Now, the answer is deceptively simple, but a lot of people get really tripped up thinking of really complicated solutions with like coordination with the backend or some sort of webhooks. Maybe the server can let you know when it's received it. No, it's literally as simple as our friend eTag. It's not really eTags, but it's the idea. So the idea is every transaction, everything, has a unique identifier. So whenever you make a purchase, you look at the data you're sending to the server and you create a UUID based on that data. So whenever you change the data, you generate a UUID. And you send that with the server, with the request to the server. And now if the server receives that, it knows that it got it, so it remembers it somehow. It puts it in a queue, in a database, doesn't really matter. And it tries to send you the response, and then it fails, and it goes, well, it failed. I don't care. The next time when you go out of the tunnel, or you automatically retry, you'll do the same request again with the same token. And the server will go, I've seen this before. And it will either not action it at all, giving you a 204, I think it is. I think I've written it down here somewhere. I don't remember these things off the top of my head. I use Google like everyone else. But the idea is you get a successful call, but is an accepted call. It's not an OK, it's an accepted call. Or a 300. Could be a 300. Check it out for yourselves. But it basically told you, I'm good. I have this. You should treat this as successful. So even though from your point of view, I failed the first time and then I succeeded the second time, you've actually succeeded the first time and silently ignored it the second time, right? And again, you can do a lot of things there. The server could literally send you a 200 as well if it decides to. I mean, technically it shouldn't, but it's not going to break the world if it does, right? So you should be aware of this mechanic. And if you have transactional operations in your app that do not send a UUID, I would highly recommend, even if it's innocuous thing, like I said, the tweet thing, check it out. It's not really hard to implement. And a lot of backends, because they're built with existing tools and web frameworks, the team doesn't even have to implement this sort of thing themselves. It will potentially come for free with whatever tools they use. So I'm talking about REST. Idempotency was the previous word, by the way. I forgot to mention it because it always trips me up when I try to say that word. Again, coming back to the previous talk about following the REST practices is because of that issue. Like a lot of middleware will basically go, you know what, you've given me that exact GET request before, and I forwarded it to the server, and the server said to me that it was okay, but I couldn't reach you. So the next time that you send me the same thing, I'm not even going to bother talking to the server. So if that happens, and your API is not built for that, again, going back to the previous example of trying to have like a GET operation for an add process, which is terrible, you're now actually in a real big problem because you're trying to perform an operation and you're getting a response that you don't expect, right? And yeah, like I said, there's a lot of details you can follow up. This is literally a blurb from that site. It tells you what idempotency is and how it actually interacts. It's a really deep topic, and it has a lot of really weird branches of logic and when it does apply and when it doesn't apply. So I would highly recommend you go and check it out. So the last big topic that we'll be talking about is service topology, which sounds like a scary word, but topology means shape, really. So this literally talks about where are your servers, how are they deployed, how do they talk to each other, what do they look like. So yeah, let's talk about where the services usually are. Like in the new world, obviously that's not the case for every every server out there, but most of the time, containers is the keyword, right? So what are containers? So what physical containers, like literally the ones you put on ships, what they did for world trade, digital containers did for application deployment, right? So the reason you can get a thing really quickly from, I don't know, like China or Russia or wherever it might be, and get it in like a few days is because of these things, those containers. What happens is a vendor will literally ship their products into one of these boxes, and the shipping company doesn't care what you have in these boxes, as long as it's legal, obviously, because they know how to move these objects from the dock to the ship. So they have like cranes that fit this style of container. They pick it up, they know where to put it. It doesn't matter what's inside it. In the olden days, people would literally load like sacks of, I don't know, like rice or things onto the ship, right? And they would have to make space to make sure that everything fit together. They would try to put like the fragile stuff on top of the not fragile stuff. They don't have to worry about any of that stuff now. So similarly, digital containers basically encapsulate an app, and they have a standard shape on the outside. And the tools that I'll be talking about in a bit know how to deploy these pieces onto basically servers. And they don't care what you've used to build your app. It could be Java, it could be Kotlin, it could be Swift. It doesn't matter because it follows the same shape. You may have seen these terms thrown around: Docker, Containerd, and Kubernetes. I picked those three because those are the most common ones. There's like hundreds more. So Docker and Containerd are basically container runtimes. They're the pieces of software that take your containers and know how to run them, right? So they're kind of important, but they're not the bit that I'm focusing on here. Kubernetes is a little bit more interesting. So Kubernetes, coming from the Greek word kybernetes, which means effectively captain, is a service kind of, let's say, deployment and orchestration. It's a container orchestration framework. It literally is the piece of software that knows how to take your containers and deploy them to the cloud. And you can tell this thing, you know what, I want, I don't know, 20 versions of this service to run. And I want them to run in 3 different countries. And I want you to redirect the traffic automatically to all of them. All of that is handled by Kubernetes. And because your services fit into these little tiny boxes, it knows how to do that without caring what you've done to write this server. Which brings us to microservices, which is kind of like a key important thing in this whole new world of building backend services. So let's talk about how we build apps, right? We have an app. And in the app, we have a database, we have our network layers, we have our business logic, we have our screens, we have our, whatever, widgets. But it's all in one app. So it's literally one binary that we ship to the client. The signer launches a process. If your database crashes, your app crashes, right? Now, you don't want that in a backend service, and you especially don't want that in a website. You don't want to go to asos.com, and if the search API doesn't work for whatever reason, you don't want your web page to crash. You want to be able to continue using the website. So how this is done in the backend world is by microservices. Each individual piece of the app, if you want to call it like that, is deployed separately as a new piece of code these days in a container, and it gets deployed as a separate thing. And then you have all these little services, microservices, talking to each other. Again, this is an incredibly simplistic view. Please don't use this as like a reference, but just to give you an idea. So in ASOS's example, the web page, the home page, the search page, the results page of the search, the product listing page, the checkout page, they're all different services that are deployed completely independently from each other. They're maintained by separate teams, which you don't have to do, but this is how we do it. And they can also be versioned differently as long as they conform to a specific API. This allows you, again, to move at different speeds. And of course, it has that problem of your app doesn't crash when part of it crashes. I'm going to have to rush through the rest because I'm running out of time. Oops. Yeah, so how does, this also allows you to do this. It allows you to deploy the same service in multiple regions in the world. So you can have your website running in the US and in the UK and in Europe, which means your clients will get to the closer version of that instance, right? And they will get faster response times. And how this is done is through DNS. So you have a domain name system. It basically is a system that you go to asos.com and it knows where to direct you. It knows the IP of the service you want to talk to, basically. So DNS is your solution to redirecting traffic to different parts of the world. I will definitely have to jump through the next slides really quickly and just give you a very brief overview of what terms are. And hopefully you will download the slides later on and read them. So clusters are collections of servers that are basically deployed together in a specific shape, topology, and you deploy them as, well, not as one, but they get deployed in a common area, and you get talked to the entire service stack as one thing. So when you change your DNS services, you can talk to a different cluster, and magically all your services work. Traffic managers and ingress controllers, these are the pieces of software that take all the traffic, and they know where to redirect it. So if you heard that term, that's all this is. There's nothing fancy about it. So this allows you to take URLs like this and send them to completely different machines in the world, even though they all share the same IP. Load balancers, similarly, they receive traffic and they split it between different versions of your services. So if you receive 10,000 users in 1 second, half of them can go into this service and half of them can go to another, so your app doesn't crash. Multi-primary replication is the act of duplicating databases across regions. So if you have 2 primary databases, you can talk to one, and you can guarantee that the changes you make will be replicated across the other one. And lastly, I do want to mention this because it's an interesting one. It's Chaos Monkey. Chaos Monkey is a very interesting idea. It basically is the practice of, on purpose, going in and blowing up your services. So a lot of companies do that. Like thankfully, well, not thankfully, unfortunately, we don't do it at the level that I will describe. But a lot of companies will literally go and periodically shut down machines on the cloud. They will block network traffic from their services to each other. And you do this periodically because you want to make sure that the teams build the software that they built in a resilient way. So when an actual failure happens, you don't have a problem because it always fails, right? So that's it, I think. I have some honorable mentions at the end that hopefully this is a list I didn't have enough time to go into, so don't worry about that. And lastly, we have a raffle. If you haven't seen us in our stand, in our booth outside, you can scan the QR code on the left and you will enter a raffle for £50 as a voucher for ASOS, and it will also give us your details. So in the future, if you're interested in ASOS or if we're interested in you, we might contact you. And the slides are open source. You can find them on the slide on the right, and the link is on the bottom. So I will leave this slide up for those that do want to scan it. And hopefully that will be it. Okay, well, thank you very much.